New pictures obtained by the James Webb Space Telescope have stunned researchers. Rather than expanding our perception of the universe, these pictures revealed a disturbing reality: our current understanding is lacking, and we struggle to grasp the full scope of the universe in its early stages. The hypothesis regarding the universe's origin is now being pushed to its limits, prompting new theories about its formation. The central question arises: how was the universe formed, and why does this discovery challenge even the most experienced space specialists in understanding the Big Bang and its ongoing complexities? This leads us to assess the Big Bang theory itself. Contrary to popular belief, the Big Bang was not an explosion within pre-existing space. Rather, it was space itself that began around 13.8 billion years ago, along with matter and time. This idea is based on a remarkable characteristic in physical science and cosmology: a singularity where gravity is so strong that space-time curvature becomes infinite. Today, after billions of years since the beginning of the universe, we understand that our celestial home is part of a significant cooperation. For experts, this reveals an essential part of the universe's existence: its continuous development. This shows that the universe is not moving through pre-existing space, but rather that space itself is constantly expanding. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. This was when the first radiant celestial objects clustered together to form mature galaxies. However, the speed at which these early galaxies developed remains an ongoing mystery. A major piece of data emerged from the first images captured by the James Webb Space Telescope in July 2022. Experts announced that the telescope had detected various galaxies, some of which existed only about 300 million years after the formation of the universe. Compared to the galaxies that formed billions of years later, these early galaxies were considerably smaller and less massive, which fit well with the scientific model. The density of matter in the early universe was simply not enough to form galaxies the size of those we observe today. However, the discovery of 6 amazing redshifted light spots from the James Webb Telescope triggered one of the most significant astronomical crises in recent times. These newly discovered galaxies, though similar in age to previously recorded worlds, are nearly as massive as our own Milky Way galaxy. This raises an intriguing mystery in cosmology. By examining a series of images taken by the near-infrared camera, experts identified the light sources using redshift. They confirmed that the light from these objects took more than 1 billion years to reach us, indicating these galaxies formed between 570 and 700 million years after the confirmed Big Bang. Strikingly, these galaxies were so large that they defied conventional cosmological assumptions. Instead of finding the expected dwarf galaxies, the structures identified were almost as large as the Milky Way. Upon further analysis, experts concluded that these galaxies were already gravitationally bound collections of stars with masses exceeding 10 billion times that of the Sun. One of these might even be as massive as 100 billion solar masses. Whether this possibility is true or not, the mystery remains unresolved. Even in this scenario, there would be much more mass in the early universe than previously anticipated, introducing a riddle to our understanding. These objects challenge nearly all conventional cosmological theories. If even one of these galaxies turns out to be real, it would significantly challenge past assumptions about the formation of early galaxies. Moreover, the density of matter in the early universe would need to be several times greater than previously accepted to explain this phenomenon. One alternative explanation suggests that these galaxies formed in a completely unknown manner, further complicating the cosmological picture. These discoveries and the resulting discussions are likely to lead to further examination of the Big Bang theory. Many space experts, especially those with alternative viewpoints, are frustrated and often find their perspectives disregarded in scientific journals. Even those who express doubts about existing hypotheses are frequently labeled as unconventional or peculiar. However, it is clear that even experts who still defend the Big Bang theory are continually confronted with questions that remain unanswered. Stephen Hawking pointed out that the nature of time as we know it began with the Big Bang. Therefore, this process could not have been set off by an external cause. Another ambiguous question involves the consistency of radiation and matter distribution throughout the universe. Regardless of direction or distance, we observe similar densities and distributions of galaxies, nebulae, and radiation. Modern theorists explain this phenomenon with the theory of cosmic inflation. However, some experts extend this assumption with the theory of turbulent inflation, suggesting that inflation has only stopped in certain regions like bubbles while continuing incomprehensibly in others. This leads to the possibility of multiple universes forming in these bubbles, each governed by its own physical laws. In this model, a big question arises. In this case, the Big Bang could be part of a larger cyclical pattern where the universe undergoes eternal collapse and rebirth. However, this is not the only perspective in cosmology. For example, an article published in 1955 by NASA's Big Time suggested that the universe might never have experienced a Big Bang and instead may have existed for an indefinite period. In this view, the expansion of the universe would be non-existent, and the continuous improvement of matter could give the illusion of constant growth. Another intriguing and controversial theory emerges from quantum physics and string theory. Some experiments suggest that our universe and everything within it may be a projection or a higher dimensional simulation. While this may sound like science fiction, it relates to the Kardashev scale, which measures a civilization's ability to harness energy. If a Type 3 civilization were capable of utilizing the energy of an entire galaxy, it might create a perfect simulation. However, confirming the reality of such a theory is deeply complex and speculative. Exploring the depths of cosmology and the origins of our universe leads us into profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of reality, challenging established hypotheses and prompting scientists to reconsider fundamental aspects of cosmological understanding. The discoveries of early massive galaxies suggest that galaxies may have evolved in ways inconsistent with traditional cosmological models. This challenges our assumptions about the timeline of cosmic events and forces us to rethink our understanding of dark matter, dark energy, and the evolution of galaxies. As future observations and research continue, we may find ourselves revising not only our theories about the origins of the universe, but also our understanding of space-time and reality itself. The discoveries made by the James Webb Space Telescope, JWST, challenge our existing models of galaxy formation and the overall timeline of cosmic evolution. The presence of massive, well-developed galaxies at such an early stage in the universe's history suggests that the standard model of cosmology may require significant revisions. One of the most profound implications of these findings is the need to rethink the role of dark matter and dark energy in the universe's development. While dark matter is believed to provide the gravitational scaffolding necessary for galaxy formation, the unexpectedly rapid emergence of these large galaxies suggests that dark matter's influence may be stronger or behave differently than previously thought. At the same time, dark energy, the mysterious force driving the accelerated expansion of the universe, remains one of the greatest puzzles in modern physics. If the early universe was more densely packed with matter than anticipated, it could mean that dark energy's effects were different in the past, or even that our understanding of cosmic expansion needs to be revised. Revisiting cosmic inflation. One of the fundamental principles of the Big Bang theory is the concept of cosmic inflation, a brief but dramatic period of exponential expansion that took place in the first fractions of a second after the Big Bang. Inflation explains why the universe appears uniform in all directions and why the cosmic microwave background radiation, CMB, is evenly distributed. However, the discovery of large mature galaxies at an early stage raises questions about whether inflation acted uniformly across all regions of space. Some alternative models of inflation propose that different regions of the universe could have expanded at different rates, leading to localized variations in the density of matter. This could in turn explain why some galaxies formed much faster and larger than expected. If inflation did not occur as originally theorized, this would have enormous consequences for our understanding of the fundamental forces of nature. Some cosmologists suggest that inflation may have been influenced by unknown quantum fluctuations, leading to pockets of space where matter condensed more quickly, accelerating galaxy formation.